So now we are going to talk about something very interesting. So we'll be talking about message streaming today. Okay. So now technically we know that what is asynchronous programming and how exactly queuing mechanisms or message queues actually help us to maintain our corresponding asynchronous programming altogether, right? Because at any point of time when we have a lot of load and we don't want to like cater the requests immediately, we learned about the fact that we can park the request into something like a message queue, and then these message queues can be very helpful to later retrieve it in the form of a producer consumer kind of like a pattern. Okay, so that was message queues, and we know that we have a couple of message queues like, let's say, RabbitMQ, Celery, Redis queues. These are some of the message queues that we technically have got. Okay, but technically there is a small problem that we have to cater. Let's talk about that problem. Okay, so let's say let me open up a design for something like lead code. Okay, so for a code submission platform like lead code, you can see there is a system design that we have prepared here. Okay, now just to give you a quick glimpse on this design, what we are actually doing is, if at any point of time somebody submits the code, then what's happening is that from the browser we are going to get a request to something like a submission service. That submission service is going to actually submit the code to submission DB, or you can say make an entry inside the submission DB. And then, and there's an asynchronous mechanism that we set up, that let's say once the submission, sorry, a synchronous mechanism that we set up, that once a response comes back from the submission DB, that means it's kind of like a checkpoint for the submission that you're. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60-minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our system design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Submission has been recorded. Now we are going to evaluate it, right? So this submission DB response is going to come up, and then we are going to push the entry inside a submission queue, right? Then we are going to push the entry inside a submission queue. Then, okay, now let's start putting the submission in the submission queue, and whenever our evaluator workers have some bandwidth to consume an object from this queue, they can actually consume it. Okay, this is an architecture. In this architecture, we are following kind of like a synchronous mechanism, that first a response from the submission DB is going to come up, and then we are actually going to submit a job, or you can say submit the payload to the submission queue. Okay, now with this synchronous mechanism, there are a couple of problems. What are the couple of problems? Let's start talking about it. First, this is relatively a slightly slower process. Why this is a relatively slightly slower process? Because technically there are two operations involved. And we are doing one after another. We are not doing both of the operations parallelly. What are the two operations? One operation is making an entry inside the submission DB, and the other operation is making an entry inside the submission queue. Okay, we are making two operations altogether. Okay, so first thing is, this is a bit slow, because if let's say your submission DB is having a lot of load, then maybe the response can be delayed. There can be a network lag, network latency can come into the picture, so on and so forth. So multiple network calls, that means multiple provisions of network latency. And the thing is that we are going to add our payload in the submission queue after the response from submission DB. So even if let's say the evaluator service and the workers running in the evaluator service are absolutely free, they still have to wait for the submission DB to give the corresponding response back. Okay. Now, there are more challenges just apart from this synchronous flow. What are the other challenges? The thing is that if let's say you want to optimize it, if let's say you want to technically optimize it, what are some of the things that you can do? Maybe you can parallelize the calls. That let's say parallelly you make an entry in the submission DB as well, and then parallelly you make a entry in the submission queue as well. This is an alternative mechanism that we have to think about. Cool. But before we go to the parallel operation, there is one more thing that your synchronous operation has to handle. What if you made an entry in the DB, but while making an entry in the submission queue, you were never able to make an entry in the submission queue? Why? Maybe your application server crashed, or maybe your for the timing your there was some network latency or network issue altogether. There was some timeout on the request happened. Your queues actually went down. Anything probably can go wrong, right? And the problem is that you have two requests, right? Already there is a latency, and if there are let's say there is a failure in case of making an entry in the submission queue and you try retries again, it's a lot of more overhead altogether, right? Now, if let's say you parallelize the calls, that let's say we want to reduce the latency, you parallelize the calls, then also similar problem can actually exist. That let's say what if you made an entry in the submission DB in a parallel call, but when you were trying to make an entry in the submission queue, something went wrong. Okay. When you were trying to make an entry in the submission queue, something went wrong, or vice versa. That you were able to make an entry in the submission queue, but your DB crashed due to any reason. Your DB is overloaded with some number of requests and then something wrong happened. Then your DB is going to crash altogether. Right. So when designing any system, we should keep one thing in mind always, that if there is a possibility to reduce the number of entries altogether that we are making, then we should try to somehow do it. Then we should definitely try to somehow do it. Okay, cool. So now what can be an alternative to all of this? What can be an alternative to all of this? Let's just talk about that. Okay, so I'll keep the overall system relatively very concise. That let's say you have a client. Okay, we have a client here. The client is making a request. The client is making a request to submission service. Okay, your client is making a request to submission service altogether. Okay, and this is let's say a horizontally scaled service, submission service. Okay, cool. And now what is the role of the application server of submission service? The role of application server of a submission service is that it needs to make sure that an entry goes to the submission queue. An entry goes to the submission queue. Okay, so let's say there is a submission queue here. Okay, submission queue here. So what it is trying to do, it is trying to make sure that an entry goes to the submission queue as well. And apart from that, let's say there is a database. Okay, there is a DB altogether, right? The entry goes to the database as well, right? In both of these, the entry should definitely go. Now the problem that is coming is that if we go via synchronous flow, then it is a bit slow. If we want to optimize, then there will be two parallel calls. Making two parallel calls has its own set of issues. That let's say one thing went ahead, another one failed. What will be happening in that case? So a quick solution that can come to your mind is that, okay, maybe what we can actually do is, let's say, let's set up a kind of like a black box in between. Let's set up a kind of like a black box in between such that submission service only makes an entry to the black box once, and that black box can do all of the things for us. Okay, all of the things for us. So one solution that is there, that let's say you put some kind of like a black box in between. Submission service is going to make an entry only in that black box, and then that black box handles everything for us. Another approach that can come to your mind is that if you carefully see this design, submission queue is going to be read by evaluator service. Okay, so what if let's say inside this submission queue you have the data being read by evaluator service. And let's say there is another service, let's say service X. Okay. What is the responsibility of this service X? The responsibility of this service X is that this also tries to consume the data from the submission queue and then make an entry inside the database. Okay. So evaluator service is also reading the data from submission queue. This service X is also consuming the data from the submission queue and making an entry in the database. And what we will do is we will make our entry from submission service to directly submission queue. So submission service will only make an entry inside the submission queue, and there will be two consumers who will be reading from the queue. Now here comes the catch. The catch is that most of the queuing servers that you are going to have are not going to allow multiple consumers for you, right? That let's say you have a evaluator service consumer that also consumed a payload, and then there is a service X also that also consumed a payload. Most of the message queue servers are not going to allow you that. Okay. Now a question can come to your mind is that why can't there be multiple consumers for the same queue? The problem is that most of the queuing mechanisms that you see, like let's say AWS SQS, simple queue service, they remove the payload once it has been consumed. Okay. They remove the payload altogether, right? The moment you consume it, let's say you made an entry, you make an entry inside a queue, right? You add a payload inside a queue. The moment that payload has been read by any of the consumer, that payload gets removed from the queue. It doesn't stays in the queue forever that somebody later can come up and read it. This is a property that the message queue brokers actually possess. Now, what can be a solution to this? The solution can be, hey, horizontally scale our queues. That let's say instead of making an entry into a single queue, you make an entry into multiple queues. That let's say there is submission queue Q1, which only is read by the X consumer, and there is a submission queue Q2, which is only read by the evaluator service. This can be a very straightforward solution that can come to your mind. The problem is that again, submission service has to make two entries. This is as bad as the old solution, that maybe entry in one of the queue succeeds, but other of the queue fails, right? There can be problem with that. Okay. So this solution is also not going to work a lot. And if I go with the first one, that let's say there is a black box. What kind of a black box we can have? Let's say there is a receiver queue. One more queue I put in place. This submission service adds the data in the receiver queue. Okay. And then let's say you have a single consumer. Let's say you have a single consumer C. This single consumer reads the data from the receiver, and now this consumer is responsible for making an entry to the database and the submission queue. But this solution is also as bad as making submission service only directly adding the data in the queue and the database, right? That we just added one more layer of a consumer. It is not helping us because this consumer C now in that case has to make two entries. So making these two entries is already a big challenge for us, and we need to somehow solve it. Now, what is the solution to all of this? The solution to all of this is that we need to somehow need a mechanism in which we make an entry once, but we can read it more than once. Just think about it. What if we have some kind of like a magical queue? This receiver is, let's say, some kind of a magical queue altogether. Okay. Such that the data that you add inside this receiver, can be read by two consumers, a consumer C1 and a consumer C2. Same data, same payload, right? And consumer C1 is responsible for making an entry in DB. Consumer C2 is responsible for making an entry in submission queue. Now just think about it. Everybody has to just update the data once. Nobody has to make sure that data gets added at more than one place. If and only if this receiver becomes kind of like a magical queue, because I just told you that in normal queuing mechanisms, if you remove the data, or let's say one of the consumer reads the data, that data is removed from the queue. But let's say if our queue is somehow super powered and it actually allows us the mechanism that multiple consumers can read from it, our whole problem is solved. Submission service has to just make one entry. C1 has to just make one entry. C2 has to make just one entry, right? No problem altogether. And we need to make sure that this superpower that has been given to the receiver is scalable and fault tolerant. That maybe this receiver doesn't fails to fulfill this new superpower promise, right? And that's where the concept of message streams comes into the picture. That's where the concept of message streaming comes into the picture. Okay. What are message stream systems? Message stream systems are very similar to the message queuing systems. Okay. With one big difference, that multiple consumers can read the same message. So if you remember, I talked about the fact that your queue brokers like RabbitMQ and everyone generally supports exact one or at most one delivery. Whereas message streams can support at least one delivery, that you produce the data once and it can be read more than once, or it can be read by more than one consumers. That means the same message can be read by more than one consumer altogether. This is what we are trying to sell. And if somehow we have this system available, which is scalable enough and supports this kind of a feature, then our problem is solved. And this is solved by message streams. Good examples of message streams can be Apache Kafka or AWS Kinesis. Okay, both of these are message streaming systems. Okay, both of these are message streaming systems. So, what is Kafka? Kafka, you can say, is a message streaming system. Okay, Kafka in absolutely simple terms is a message streaming system. Okay, it's open source, and just FYI, it was made in LinkedIn, right, for all the stream processing requirements altogether. The good part about message streams is that in most of the use cases where you were using a message queue, message stream just fits extremely well. Apart from that, if you carefully talk about or mainly talk about Kafka, then Kafka is very highly scalable, highly durable, and delivers extremely high performance. Okay. It's specifically engineered to make sure that you are able to work on high scale and high amount of data. If you have to handle a humongous amount of data coming towards you, you have the solution as Kafka. So Kafka works very well for the scaling mechanism, and we'll talk about the overall internal mechanisms, that how Kafka works and how you set up things with Kafka. But overall, this is like, if the question comes at scale, Kafka is a no doubt one of the most scalable systems altogether for its own use case, that is message streaming. Okay, so now what will happen if, let's say, you introduce something like Kafka here? So if you introduce something like Kafka, then your whole point of keeping a submission queue can go out altogether. Why? Because what Kafka is going to support, Kafka is going to support the fact that you can make one entry inside Kafka and multiple consumers can actually read from it. That means your architecture is going to change a bit. You do not need your submission queues anymore. Why? Because your submission queues were eventually read by evaluator service. So what you can have is, you can have Kafka setup here, right? You can have Kafka setup here. Now, a good thing about Kafka is that it's extremely durable and highly scalable. What your evaluator service can do is, your evaluator service can now directly read the data from Kafka, and your evaluator service can become a direct consumer of Kafka. Okay, your evaluator service can become, I'm writing it as eval service, can become a direct consumer of Kafka. And what you can do is, you can have one more service, or let's say you can even make your submission service as a consumer as well. So let's say your submission service is also a consumer from Kafka, which later reads the data from Kafka and makes an entry in the database. Or you can have a separate consumer altogether which reads the data from Kafka and makes an entry in the database. Now, theoretically, what can happen is that if you make an entry in Kafka, it can stay in Kafka forever. So that means we can definitely for sure assume the fact that if submission service has produced the data in Kafka at a moment, we can successfully record the fact that, okay, your submission has been received. You do not need to wait for a DB entry to be made before you respond back to the client. Okay, before you respond back to the client, because of the fact that Kafka is extremely durable solution altogether, right? Why do we even need to make an entry in the DB if you have that question? So that question can be simply answered with the fact that later, let's say you want, if the user wants to see their submissions or older submissions or do some manipulations altogether, then those calls can be directly responded back from the database, because of course you can keep things in Kafka forever, but generally you do not. And we will talk about how exactly consumers read the data from Kafka. So you will realize that the use case that clients have to see their older submissions has to be resolved from database only. Why is that? You will get an answer in a moment. But the thing is, just submission service does not have to now wait for an entry to be made in database. If you have successfully made an entry inside Kafka, you can be rest assured that your entry will be eventually made inside the database by the corresponding consumer. That consumer can be a separate service, that consumer can be your same submission service also, no problem. But if an entry has been made in Kafka, you can be rest assured that it will eventually definitely go inside your database, and you can immediately respond back to your client that we have recorded your submission altogether. Now let's start talking about how exactly Kafka handles things altogether. So if you want to understand Kafka, right, I'll be also doing a small demo in front of you. There are a couple of terms that you first of all need to clear in your head. There are a couple of terms that you need to first of all clear in your head. One term is producer, one term is consumer, one term is topic, one term is your partition. Let's call it partition. Okay. These are kind of like the four most important terms that you have to understand. If you do not understand them, you are not going to be able to answer any corresponding questions around Kafka, because Kafka is one of those topics in your infra interviews or system interviews or data interviews where you have to all not just say that, okay, I'll introduce Kafka here and things will be automatically done. People will expect you to understand that, okay, what will you do with Kafka? How will you set up things with Kafka? How exactly things will be managed altogether, right? So this is going to be something that you have to answer. So it's not like you just need to know that there is a very scalable system, very scalable message streaming system called as Kafka, which if we will introduce will solve the scalability problem for you. You also need to know how will you set it up or what solutions you are going to prepare. Okay. These are the four terms that you have to understand. So let's try to understand everything one by one. And if you want to understand Kafka at every point of time, you need to have understanding of basic queuing systems or basic message queues. Okay. Now what happens in a basic message queue? Let's say this is a basic message queue. Okay. This is your any message queue altogether. In a message queue, what happens is, let's say you have payloads, right? Let's say you have payloads like this. Okay. And these payloads are added inside your queue. Okay. These payloads are added inside your queue. Now, who adds these payloads? Who adds these payloads? The payloads are added by producer. The payloads are added by producer. So producer is the system. Producer is the system who is actually responsible for putting these data or putting these. A lot of time in Kafka, this is also called as events, or sometimes it is also called as payload, or sometimes it is called as your data or your message, anything you might find people calling it. But in a nutshell, producer is the system who is responsible for putting the data into your queues, right? Now the same definition of producer goes with Kafka as well. In Kafka, whatever data is going to be created, that is going to be created by the producer, and whatever data is going to be read, that data is going to be read by the consumer. So consumer is going to be responsible for reading these events and reading this data altogether. Okay, for reading these events and reading this data altogether, the consumer is going to be responsible. Okay, so now how exactly topic and partition comes into the picture, let's start talking about that. And for that, let's take a very simple example. Let's take a smaller, like, let's take an example where Kafka can outshine a lot of other solutions altogether. Okay, for example, let's say there is a application like Uber. Okay, assume that there is an application like Uber. One of the fundamental operations in the application like Uber is updating driver locations. This is kind of like a very fundamental operation that any ride sharing or ride app like Uber, Ola, right, they have to maintain. Because if you cannot maintain latest driver location, or you cannot record latest driver locations, then most of the things in application is of no sense, right? Your user will not be able to know when the driver is going to come. You will not be able to calculate how much time the driver is going to take in order to reach the location to pick up the user, or how much time there is left in the ride to complete, right? So a lot of things is dependent on updating driver locations. Now, how exactly you think you would like to update driver locations? One is, there is a driver mobile app. Probably there will be a driver app, right? And driver app, assuming it's Android, right? It has capability of fetching the latest location, right? Any client that you see, browser, you see Android, you see iOS, most of the client has the capability of fetching the current geolocation. So fetching the current geolocation is dependent on your client. So we do not need to discuss how do you fetch the geolocation, right? Somehow, let's say the geolocation has been fetched. Now you need to record this data, right? You need to record this data. So this driver app is going to, let's say, hit your server. This driver app is going to hit your server. Now, do you think you are going to just directly from your data, from your server, directly update the database for the latest location of the driver? I don't think this is going to be a good solution. Why? Because think about at scale of Uber. There are probably more than 3 to 4 million drivers altogether in Uber, most probably in a specific region. If you consider, let's say, the South Asia Pacific region, there will must be definitely more than 5 million odd Uber drivers, maybe more, right? I'm assuming that in India also, most of the 4 to 5 major metro cities have Uber. Then you have countries like Pakistan, then you have Bangladesh, right? Some part of Singapore. So definitely more than 5 to 10 million we can assume as a good figure. And assuming the fact that this whole region has the almost the same time zone. So if you consider that at peak hours, peak office hours, all of the drivers must be moving. If all of the drivers are moving, then we need to actually populate, or we need to actually record their latest live location very frequently, right? Generally it should be like every 10 seconds or every 5 seconds you would like to know your driver's updated location. So every single driver app is going to bombard your server with humongous number of requests. And let's say you are able to scale your server with all of those requests, no problem. But do you want to put all of those bombarded requests to your database? Probably not. Probably not. Right? Your database is relatively more, I would say, crucial for you. Plus, plus, there is one more issue here. You do not just need your driver's latest location. You probably need your driver's complete location trace, right? You do not just need your driver's latest location. Probably you do need your driver's complete location trace. Why? To track. Sometimes that users raise dispute that my driver took a separate route. For that you need to know the route. For that you need to know the route, that what route the driver actually took. For that you need to have the location data of the driver throughout the trip, right? So it's not just about updating your database with the latest location. It's also about recording all the corresponding events, all the corresponding latitude and longitude changes. So let's say if you thought that, okay, this server is going to have a lot of requests, and all of those requests, instead of sending them to a database, I'll just introduce a message queue. I'll just introduce a message queue in between. And that message queue is going to read the data, or let's say server is going to just produce the data in the message queue, and slowly and steadily we can have a consumer that can later update the database so that the database is not bombarded immediately. But this also doesn't solve your complete problem. Why? Because your normal message queues cannot keep your data forever. The moment consumer reads the data from the queue, then that data is gone from the queue. Plus, you also need to make sure that this queue is highly scalable. This is where things like Kafka outshines everything. What you can actually do is you can set up queue using Kafka. You can set up a Kafka queue. Okay. You can set up a Kafka queue. Okay. Now, what Kafka ensures is that even if a consumer has read the data from Kafka, that data still exists in Kafka because there can be other consumers. So let's say there is one consumer, which is, let's say, a location consumer, which is reading the data from Kafka. And let's say later there is some another consumer, which is, let's say, um, trip analyzer consumer, which analyzes how the trip actually went altogether. That is also reading an event from Kafka, right? So first problem that Kafka solves here is that your driver location is not just required to be updated in the database. Your driver location can be required for multiple reasons. Updating location or getting live location, plus analyzing the trip, that what went wrong with the trip or what went right in the trip. Plus, you might need some more analytical data, that you might need to analyze that, okay, probably in a particular route, right? What is the total time? So that means that now there can be multiple reasons that whatever your data is that you are technically collecting, that can be read by multiple consumers. Okay. But there is more to it. Just think about it. Let's say there are approximately 10 million odd drivers. And let's say there is a single queue. There is a single Kafka queue that you have. If all the 10 million driver requests will be bombarded to the same queue, right? Because let's say your server is horizontally scaled, but from your server, when you are actually adding the data to the queue, if there is a single queue, then if you will bombard all of your requests to the same queue, then what can be the problem? The problem can be that even this queue can be overwhelmed, right? If you have a single queue, then the single queue can be overwhelmed, right? It's not prone to issues like throttling. Okay. So that means it's a simple issue of what? It's a simple issue of scalability. And we know how to solve scalability issues, right? We have been solving scalability issues for quite some time now. So we know how to solve a scalability issue. So one way would be vertical scaling, but that has a limit. Another way would be horizontal scaling. And Kafka by default supports it. Kafka says that, hey, there is a highly likely chance that this queue might need horizontal scaling. That means you might need multiple queues to store your data, right? You might technically need multiple eventual queues to store. And this is not just like a normal queue. I'm just referring to it as a queue just because you are able to relate it with your regular message queues. Okay. Now, let's say you have n number of these kind of queues. Now all of your requests can be distributed into these n number of queues, right? In this way, what will happen? You will reduce the amount of load that was probably gonna come on a single queue. And these set of queues are eventually called as partitions. This is what we call as partitions in Kafka. Partitions in Kafka. Okay. This is what we call as partitions in Kafka. So you can say that partition is kind of like a out of the box solution. Partition is a kind of like a out of the box solution that Kafka supports in order to make sure that you are able to distribute your data in a horizontally scalable way, right? Right. And a collection of these partitions together, let me put it like this. A collection of these partitions together can stay, and you can define, let's say you can have, let's say, a hash based partition, that let's say you are trying to create a partition based on the hash, right? Let's say all the riders who actually qualify for hash 1 are going to add their payloads here. All the riders who qualify for hash 2 are going to add their payloads here, and so on, right? And so on. This is what will be the concept of partitions inside Kafka. So in when somebody is discussing with you things about Kafka, they can actually ask you that probably what will be the partitioning key that you would like to keep. What can be the partitioning key that you would like to keep? Okay, and that will be kind of like a logical answer based on the system that you are actually thinking about. Okay, that will be kind of like a logical answer that you have to think about. Okay, so let's say for our use case, let's say Uber is not, let's say, a global service. Let's say we are looking at something more regional like Ola, right? So Ola is just in the regions of India. In that case, one good way of keeping the partitioning key can be on the basis of the region division or the state division that you have in India, right? Or maybe even granular level city, that let's say you have too much amount of scale to handle, then maybe based on the city that you are actually coming from, right? And so on. So this can be dependent. Let's say there is kind of like a live streaming that is happening, right? And you have to record the score that is happening for your match, right? Let's say there is a India Pakistan match going on, and then there is, let's say, an Australia England match going on for World Cup, right? In that case, whatever is your match or the unique match ID, right? Whatever is the match or a unique match ID that you have, that can be your partition key. So it can be dependent on what kind of solution you are building, right? Also, keep one thing in mind. I'm just, for oversimplification, calling this as a queue. For oversimplification, I'm calling this as a queue. It's not exactly a queue. What it is, we are going to talk about it. It's not exactly a queue. What it is, we are going to talk about. But for simplicity, so that you are able to map things with your regular message queues, I'm explaining this in a way. Okay. Now, just think about it. For a system like Uber, driver location is not the only thing that probably you would like to store in Kafka, right? Maybe at any point of time, whatever ride requests you are getting, that also you would like to store in Kafka, right? That, let's say, what type of ride requests you are getting, because based on that you will be able to eventually calculate your pricing. Your pricing model can be calculated based on that. That, let's say, if from a particular region you are getting too much ride requests, or for a particular destination you are getting, let's say there is a big concert that's going to happen, so there is a highly likely chance that a lot of people are going to book cabs for that particular area, right? So for that also you need to have all of the data, and let's say you would like to store that data also in Kafka. So what you can do is, you can have a group of separate partitions altogether, right? You can have another group of partitions altogether coming up, which can store some other type of data. Okay, so let me denote it with another color. Okay, right? And this will be another partition for you. This will be another partition for you. Okay, set of partition for you. And this is where the concept of Kafka topic come into the picture. You can say, for one type of data or for one set of partitions, you have one topic. So this will be one Kafka topic. This will be one Kafka topic. And let's say we call this topic as driver location topic. Then this will be another Kafka topic, which will be your ride requests topic, and so on, right? So a topic is eventually going to store all of the data about one event, right? All of the data about one event, right? So one type of a event goes to one topic. Now inside that topic there can be multiple partitions. So based on your partitioning logic, one of the partition will take that event. But for different type of events, you have different type of Kafka topics. Okay, so it's kind of like your user defined category. It's kind of like a category for you, just like in e-commerce you have categories, right? Electronics has a category which has a lot of products, right? Then your kitchenware is a category that has a lot of products, right? So you can say that category that you have is kind of like your Kafka topic. That category that you have is your Kafka topic. So you can have some formal definition. Look, you can very easily Google about some formal definitions. So let's check out for that. So if you search for Kafka topic, okay, and you can see Kafka topics are categories to organize your data. Kafka topics is category to organize your data. You can see a very interesting image we have here. So you can see you can have one topic can have multiple partitions. You can have another topic, that topic has another partition. You have another topic that have another partition, and so on, right? So let me explain. So inside your Kafka server, or you generally call it as a Kafka cluster, right? Okay, let's say this is your Kafka server. Kafka server. Your Kafka server is going to have topics and partitions. One topic has multiple partitions. This also line you can keep in mind to understand it better. One topic has multiple, or can have, or one topic can be having multiple partitions. Okay. First of all, keep this thing in mind that topic is an over level thing and topic has a partition, right? Now, what is a topic? Topic is like a category. Just think about it. If you remember in this lead code solution, we had two type of queues, right? One was recording submission related data. One was recording evaluation related data. So if you think with the world of Kafka, evaluation is going to be one topic, submission is going to be one topic. And these multiple queues that we were maintaining is going to be kind of like partition that you can think about, right? This will be your corresponding partition. Now here, everything you have to manage yourself, right? Here you have to manage yourself. But in Kafka, if you do the right set of configuration, you do not have to manage a lot of things yourself, right? Why? Because Kafka says that you define a topic. That means you define a category. So one category can be driver location. Driver location can be read by multiple consumers. Okay. Then one category will be ride request. Ride request can also be read by multiple consumers. You just define a topic. Inside the topic, you can configure the number of partitions that you want to have and the logic based on which the partition needs to happen. Now, whenever a producer has to produce some data, the producer needs to tell which topic they want to add the data to, right? So the producer will tell what will be the topic. So producer will tell whether you want to add a driver location, so it will go to the driver location topic. If you want to add to ride request, then it will go to ride request topic. And then once it enters the topic, then the logic of partitioning comes into the picture. That there are multiple, let's say Kafka queues. Again, I'm telling that I'm oversimplifying by the word queues. Okay. So let's say there are multiple Kafka queues. Which queue the data should go to will be defined by our partitioning logic, right? And you know already about partitioning, what partitioning is, how partitioning works and everything, right? All of that concepts that you might have read in databases, everything comes here in a similar fashion. Why do you need partition? Because the same amount of data will be distributed across multiple servers and all of that stuff. But the main thing is, topic is kind of like a collection of partitions, or you can say a topic has many partition, and a topic defines a category, right? So if let's say you were doing everything with message queues and not with Kafka, then in message queue you would be taking one queue for a let's say one task, right? Let's say there is a queue in your, let's say you have an e-commerce app. You have one queue that records all the emails that needs to be sent, right? Then let's say there is one queue that records all the order updates that needs to be registered. In the world of Kafka, you will be having a Kafka topic of emails, and you will be having a Kafka topic of order management, right? So one topic will be generally for one type of a category of data or a type of a task. And inside one topic, there can be many partitions so that you can horizontally scale your topic. And there can be multiple consumers that can read from a topic. That concept still exists per topic. So multiple consumers can read from the same topic. Multiple consumers can read from the same topic. This is also something that you have to keep in mind. So if let's say we go over the terminologies once again, you can say topic is a logical group or category, which has a lot of partitions. Okay. Topics, or we should say, we publish the data to a topic and subscribe the data of a topic. Any kind of a publishing subscription, everything we go with topic. So this is what topic is. Okay. And then you have partitions, right? This is actually a partition that I'm again and again referring to as a queue. This is what we call as a partition. Okay. This is what is a partition. Okay. This is what is a partition. Okay. You can say partition is a immutable sequence of events. Partition is a immutable, it's an immutable sequence of append only events. Okay. Think about it like a file. Think about, now again and again I was saying the thing like it's kind of like a queue, but it's not exactly a queue. I am just oversimplifying it. Now let's try to understand how exactly this partitioning works. So every partition is kind of like a append only file. Okay. It's kind of like a append only file where whatever event or message is going to come up, it appends that to a partition. Okay. Whatever event or whatever message you are going to actually get, it's kind of like append that to your corresponding partition. Okay. Whenever you are going to produce some data, whenever you are going to produce some message, right, and it is sent to a Kafka topic will decide which partition you need to record it to. And then these partition act like a file where you append your data altogether, right? You always add a new data altogether, right? And if you see how a message looks like, this is technically your message. Okay, this is your message or an event in Kafka. How a message or event looks like, it's kind of like a key and a value pair. You have a key value pair. Along with that, you have timestamp. And a few extra properties inside a header that actually gets appended. Okay, and a few extra properties inside your header that actually gets appended, right? And you can actually decide on what kind of a what particular format you will be able to add key value pairs and everything. We'll do all of those demos after some time when we have more context on what are the things that Kafka can actually do, right? But overall an interesting property that comes here is immutability. Immutability means that at any point of time you have written your messages, you cannot later alter it. This gives your durability aspect to Kafka, right? This gives durability aspect to Kafka, that once you have written your message in this sequence, you cannot later alter it due to any particular reason, right? This is something that you have to always keep in mind. So a question can be in your mind that can we delete these events or can we delete these messages from Kafka? So you have to define a retention policy, because you can see this is more or less like a log file kind of a system, right? So you can define your retention policy that for how much amount of time you want to keep the data inside Kafka. You want to keep it for 7 days, 30 days, 90 days, whatever you want to keep as the retention policy, you can keep that. And after that particular amount of time, your data is going to be removed. Okay. You can also define retention based on the size, that if you want a particular upper limit for the size, then you can do that. Okay. You can manually also make sure that you are able to forcefully delete, but for that you have to manually come up to the login to the server and like forcefully delete things. But just like how retention policies can be configured for a cache, you can have a retention policy for Kafka. That's why Kafka is extremely good systems, and it actually came up with storing logs only. Like LinkedIn has to maintain a lot of logging mechanism. That's when they defined the whole infrastructure for Kafka. Because if you see any log systems or log infrastructures, then there are a lot of systems for which you need logs for, let's say, 5 or 7 days. But there can be systems that you need logs for 90 days. There can be systems for which you need logs for, let's say, last 4 years, maybe, not sure, right? So you need to have kind of like a this kind of a append only mechanism where you can define your own retention policy. So that retention policy you can actually define in Kafka, and then based on that your events are going to be eventually removed, whatever you define on that, right? Is there any upper limit to the time? I am not sure about that. You can check, because these things can vary approximately around with every version. But if you see theoretically, then you can have a very big amount of time for which you can retain the events, right? And that's where the beauty of Kafka actually comes into the picture. So what happens is that in a Kafka partition, when you have some data, D1, D2, D3, assume that, let's say this is a Kafka partition, then what you can have is you have consumers. Okay. Now this, as I mentioned, it's not a queue. When we were understanding, we were thinking that it's kind of like a queue, but it's not a queue. It's kind of like an append only file. If it is an append only file, that means if there is a consumer 1, and let's say there is another consumer 2. Okay. Consumer 1 reads from the partition, and consumer 2 also read from the, or let's say consumer 1 reads from the topic and consumer 2 also reads from the topic. They do not remove the data, because it's not like a queue where you can dequeue stuff. They do not remove the data. So it's kind of like they maintain something like a offset. What is an offset? Offset defines that what is the last entry point you have actually read, and then based on that offset they move ahead. So let's say consumer 1 has read up till D2, so you can define inside consumer 1 that next time when you read, do you want to read from the next available data, or you want to again read from beginning? You can define that, okay, every time a consumer should read from the beginning to the end, or every time the consumer should read from wherever they left last. So let's say consumer 1 has read D1, consumer 1 has read D2, and consumer 1 has read D3. It's going to move ahead. It's kind of like an offset based system. They do not remove anything. That is how consumer 2 can later come up and also read D1, D2, and D3 later, whenever consumer 2 has some time. This ensures multi-read policies inside your Kafka, that one data published inside a Kafka topic can be read by multiple consumers, because eventually the consumers do not remove it. If the consumers do not remove it, multiple consumers can iterate. So it's kind of like an iteration based mechanism. It's kind of like an iteration based mechanism. And every partition maintains these offsets, which is kind of like a sequential identifier for your message. It's kind of like a position, or the kind of like, just like how you see arrays indexes where every index gives you kind of like a position. It's these offsets are like that. And when consumer read these messages, they can remember what is the current offset that they have read. Okay. And the best part is that consumer keeps on committing that what was the last offset that we have read, so that they can come up later after some time and read from the remaining set of data. Just think about it. Let's say consumer 1 read up till D4 and everything was good. After some time, new data was published. D5, let's say after an hour, D5, D6, D7. So now when consumer 1 has to resume the data reading, then consumer 1 has already committed the last offset that it actually read, and then it can resume after that. So it will resume to D5 once it has some time. Okay. So in this way, you can actually read from wherever you left off, or you can also say that, okay, every time read from the beginning. I don't care. Every time read from the beginning. That is also something that you can define. So now we know a couple of things about Kafka. We know about like basics of Kafka, that what are the things that exist with Kafka. Now, from here, if you want to understand some more internal concepts and some more advanced concept, that let's say how horizontal scaling can be done in Kafka, what are brokers and all of that. Before that, it's necessary that at least we know how to set up Kafka so that we can at least play around with the concept that we are going to learn. How can you set up Kafka? Easiest way to set up Kafka can be using Docker. Okay. Easiest way to set up Kafka is using Docker. Okay. So you can find a lot of, I would say, setup articles where you will find people setting up Kafka. Okay. I will also push, let's say, a GitHub repo. Okay. All you have to do is you can just clone this repo. So I'm creating it for the fact that you do not have to go to any articles and you can just come up Kafka Docker setup. Okay. I'm making a repo, create repository. And inside this repo, I'm going to make two files. One is going to be a Docker compose file and one is going to be a README file where I will add the commands that you can use to interact with Kafka. So first of all, let's add a README. Okay. Kafka Docker commands, or let's say first of all, Kafka Docker setup. Okay. So if you have to set up, what are the commands that you need to execute? So first of all, you need to clone this repo, clone this repository, then execute or move inside the cloned directory and execute the following command. Execute the following command. Okay, so because it's going to be a Docker file for us, right? What we are going to do is we are going to have a Docker file inside which I have the complete configuration that you need for setting up the latest versions of Kafka, right? So what you need to do, you need to clone this project up. You need to clone this project up. And once you have cloned, you need to go inside this project and then you have to use a Docker compose up command, right? This Docker compose up command is going to make sure that you load everything from your Docker compose file and start a Docker container. So you have to use Docker compose up minus D. This is the command that you have to execute and your container will be up. Okay. So let me add the Docker file as well and I'll show you as well. Okay. So let me do one thing. Let me add create a new file. Okay. And the file name is going to be your docker compose.yml because you have to always make a Docker compose file in order to make sure that it takes all the configuration from your Docker, right? So this is the file I have already, like I already verified it from one of the premium articles. So you do not have to worry about whether it will work or not. It will definitely work. All you have to do is just make a docker compose.yml file, commit the changes. If you want to understand what is going on here, you can read about this configuration later, but that's not going to be necessary. Now, all you have to do is just clone this repo. So let me open my terminal. Okay. So I'll go to my developer folder and I'll say git clone and I'll clone this repo. You can see the repo has been cloned. And now you have to execute the command docker compose up minus D. The moment you do that, it's going to handle everything for you. Okay. Now, can you see what it is saying? Docker daemon is not connected because it's checking whether Docker is running or not. So you need to make sure Docker is running in your system. So let me turn up my Docker, right? So I'll add this to the README as well, right? That you need to keep the Docker desktop running, right? So I'll just quickly edit the README. Make sure Docker is running. Okay, make sure Docker is running. And I believe in a moment Docker should be up. Let's wait. Okay, cool. And now I'll execute the command again. The moment you do that, you can see it is going to create a container. If you have already created a container once previously, then it will not take a lot of time because it must have already pulled the image, just like how it has pulled the image already in my system. But if you are executing this command for the very first time, then it can take some time. For example, I can even show you. If I remove this image from my system, Okay, we have to delete the container it is using. So let's delete this container. So if you will do it in your system, I'll show you how it will look like. Let me delete it forever and I'll execute that again. And now you can see it's for the first time now pulling, because now the image I have deleted. So you can see now it's pulling for the very first time. Okay. What I run was Docker desktop. I turned up Docker using Docker desktop. Okay. Cool. Now you can see with this particular command, everything is ready. Now we have a Docker container which is having Kafka running end to end absolutely fine inside it. Okay. Now let's say we have to connect to the Docker container. Then what we can do is I'll open two sessions. So I'll open one more terminal session. Okay. You can execute a command docker exec -it means interactive, and we can go inside /kafka/bin, right, and try to access the shell. So this is the command that you can use to open the interactive shell of Kafka. This is kind of like the Kafka console that we can interact with. Okay. Now once the container is up, use the following command to enter the Kafka shell running inside the container. Okay, you can run the following command. Okay, don't need to worry about these commands. You can just read how Docker commands actually work, and this will work for you. And you can see you have Kafka console actually up here. And if I execute the same command from a different terminal as well, you can see I'm up inside here as well. Okay, this is working absolutely end to end fine. Right? Cool. Now, there are multiple provisions in which you can actually see what all topics do you have. Okay. And you can even create a topic. So you have to actually execute dedicated Kafka commands to create a topic and to actually list down all the topics or add an entry into the topic. These are just regular Kafka commands. 99% of the time, if you are interacting with, let's say, something like Python, C#, Java, Node or something, there will be packages using which you will be doing all of this. But if you are interacting with directly with the shell, then you have to execute these commands in order to create a topic or do something. Okay. So for example, if you want to create a topic, you can say /kafka hyphen topics.sh. So there is a file called as kafka topics.sh, which has all the configurations or all the code which is required to create a topic. You can give a flag --create --topic. So we want to create a topic. Okay. And then you can give the name of the topic as sample topic. Okay. And then you have to give a flag bootstrap -server broker : and you have to give the port. So you need to give 29092, I guess. Okay. The moment you execute this, one second, it's 9092. Let's see which port it is actually running with. Okay. Oh, my bad. Bootstrap spelling is wrong. This should be bootstrap, not botstrap. Bootstrap. And you can see created topic, sample topic. Created topic, sample topic. Okay. As simple as that. So this is just a command that you have to execute if you want to create a topic. So if you want to create more topics, you can have more commands executed in order to create a create more topics altogether. Right. Now, let's say if you want to list all, and again, you do not need to remember all of these commands. The best part is you do not need to remember all of these commands, because a lot of times you might not be even interacting with the terminal, right? Right. So if you are using, let's say, something like Python, you just need to see in your Python library what is the corresponding function that does that for you. Okay. So let's say if you want to list, and let's create one more topic. Let's create one more topic. I'll call it as user topic. Okay. User topic. And you can see one more topic created. Now, if you want to get the list of all the topics, then you have to change this command a bit. Now you do not need to give the --create flag. You do not need to give the --create flag. Okay. All you have to give is, let's put a space here. All you have to give another flag called as --list. If you give --list, you can see both the topics are being listed. These are the two topics that are present with which we can probably play around. Okay. Now, let's say I want to start my consumer, that let's say let's have a consumer that can start reading from a topic. Okay. So we have a topic, sample topic, right? So in another terminal, I'm saying dot slash Kafka console consumer. So there is a, when you set up Kafka using Docker, Kafka gives you a console based consumer which has all the logic for the consumer written in shell script. So this is the file Kafka console consumer.sh, to which you need to tell which topic you want to consume to. So let's say sample hyphen topic I want to consume to, and you can tell, do you want to consume it from the beginning or you want to give a proper offset? So let's say I'll say from beginning. From beginning, I guess the spelling is correct. And then you have to give your server configuration, which is minus minus bootstrap hyphen server, and then you have to give broker colon 29090. Okay. The moment you do this and press enter, you can see nothing is happening. Why? Nothing is happening because there is nothing in the corresponding topic. As simple as that. If there is nothing in the topic, nothing will be consumed, right? So that means we need to probably create something in the topic or add something in the topic. So for that, you have Kafka producer or console producer, as far as I remember. Console producer. I'll put all of these commands in the readme, don't worry. .sh. So this is the file which has all the logic to produce something in Kafka. You just need to give it a flag topic, sample topic. Okay. You need to give your server configuration. So bootstrap server broker colon 29092. Press enter. And now you can start producing some data. Okay. Also, by default, there is some basic set of partitioning already done. So I'm not demonstrating partitioning as of now, but I'll show you partitioning and how to add more partitions, all of that later. But first of all, let's try to understand the basic of setting up things with Kafka. So here, let's say we just produce some random strings. So hello world. Okay. I added hello world. And then let's say I added something like Sanket Singh. Then let's say designing systems. Okay, we added some data here. We are producing some data here. Okay. Can you see, without any effort, the consumer is already consuming the data for us? That's why I opened two parallel consoles. In this console, I'm producing the data. Let's produce more data. Bye bye. This data has been consumed by the consumer. So you can see your producer consumer logic is working absolutely great, right? And if you stop producing, the consumer will keep on listening that, okay, as of now, we have nothing more, right? We don't have anything. But as I mentioned, from the same topic, multiple consumers can read. So let's open one more consumer. Okay, let's create one more consumer, right? So I can execute the command, go inside the shell, and then create one more consumer which can read from the beginning, right? And you can see this is another consumer which is reading all of that data, which has been already read by consumer number one. Isn't that pretty good? Okay. And you can learn about this bootstrap server flag. Okay. Bootstrap server flag Kafka. Okay. You can see like what it actually does. So whatever server you have configured, it tries to select a server from the corresponding set of clusters. What is Kafka clusters and everything? I'll talk about that later. What is a broker, how broker converts to a cluster, all of that I'll talk about. Okay. But let me add these commands. To add a topic now, to add a topic in Kafka, we can use the command, this one. Okay, this can actually help you to add a topic in Kafka. And then to start a consumer on a topic, we can do something like this. We can start a consumer with this command. Okay, make sure you start a consumer in a new terminal, otherwise you won't realize the difference, because you produced something, then exit, and then consume something. It will not look that seamless. So make sure you add it in a new terminal. And for producing the data, you have to use this command. To produce the data, in the topic, you have to use this command. And that's it. This is more or less the things that you technically need. Okay, so these are the commands that if you will use, you will be able to do your first interaction with Kafka, right? That you are able to create a topic, right? And then apart from just creating a topic, you are able to produce some messages inside the topic, right? And then you will be able to consume messages from the topic, right? This will be kind of like the basic set of stuff that you will be able to do, right? And this is something very important, right? This is something very important, right? Why? Because if you will not see this actually happening, you will never realize, okay, that okay, it's kind of like an append only file, but internally it's kind of like helping us as a queue as well, because this is what queues were doing for us, right? Somebody adds data in the queue, somebody consumes data from the queue. So it can, that's why it can be a replacement for your corresponding queue. Okay. And apart from that, you can even describe some details about the topic. You can see some details about the topic. Okay. So in the same file, Kafka topics.sh, right? And if you give your server config, there is a command called as minus minus describe. If you do a minus minus describe, you can see a lot of details about your partition is actually coming up. Okay. But if you give, let's say, minus minus topic and tell a specific topic to describe. So let's say sample topic. Sorry, my bad. Spelling is wrong. Sample topic. You can see these are the details of your topic. These are the details of your topic. Okay. That for now, that for now, you just have a single replica, right? There is one leader. So you can see there is already some sense of horizontal scaling that it is doing. Okay. How you can configure it, how you can add more replicas. We'll talk about it. There is as of now no partitioning done because we have not introduced any logic, right? So by default, everything is going to kind of like the same file, right? Whatever data you add, it goes to the same file altogether. But later I'll show you how you can add more partition. But this is a command with which you can get some basic description about corresponding set of I would say topics. And here, if you just directly give this command, it will try to explain all the topics that you have. So there is a user topic, there is a sample topic. So if you want to explain all the topics, you can get that there. Okay. Just understand one thing. Now, because of the fact that your data is always present in the topic, you can replay whatever happened. So let's say if you want to replay the complete ride of an Uber driver, that where exactly the driver went altogether, you can replay that because you have set up the retention policy that whatever you have added in the driver location topic stays there for, let's say, an year. So for an year, you will be able to actually see that, okay, this particular, what actually happened throughout the movement of a particular ride inside it for a particular driver, right? So technically Kafka does a lot of things for you apart from just publishers and subscriber model, that you're able to publish an event and you're able to subscribe to event. It actually does more than that. It has very high throughput, extremely scalable, right? Multiple consumers can read from it. So lot of things can be done here.